Education for Excellence program, Automatic Transmissions, Principles of Operation, is designed to familiarize the technician with the basic concept involved in the mechanical and hydraulic operation of an automatic transmission. We will begin by explaining the three mechanical functions of the automatic transmission, the first of which is the method used to disconnect and connect engine and driveline. The second mechanical function is providing the required gear reduction to smoothly move a vehicle from a dead stop up to cruising speed. The third and final mechanical function is changing the normal direction of rotation so that the vehicle can be moved in reverse. Looking at the first requirement of connecting or disconnecting the engine from the driveline, we find that vehicles with automatic transmission use a type of hydraulic unit, which in its most simple form is referred to as a fluid coupling. The principle applied in the operation of a fluid coupling can be illustrated using two electric fans. If one is plugged in, as it increases speed, the resulting air velocity will cause the other fan to begin to turn. Finally, the second fan will turn at nearly the same speed as the first, even though no direct mechanical connection has been made. The air velocity acts as an effective coupling mechanism. A fluid coupling uses the same principle, but with fluid rather than air, since the density of fluid makes it more efficient. In a fluid coupling, the fan providing power is part of a metal housing, which is attached to the crankshaft of the engine. The metal housing is filled with fluid. The second fan is attached to the input shaft of the transmission and is suspended in the housing. Just as the electric fans in our example, as engine speed is increased from idle, the fluid within the housing will cause a coupling effect to begin between engine fan and transmission fan. At a given speed, dependent on the design of the unit, full coupling will be in effect, and both fans will turn at nearly the same speed. A refinement to this principle involves the addition of a third fan. The third fan redirects the fluid to provide torque multiplication. This design is commonly referred to as a torque converter and is used in all modern applications. As mentioned at the beginning of this program, the second requirement of the transmission is to multiply the power provided by the engine so that it will move the dead weight of the vehicle from a standstill smoothly up to cruising speed. This can be done by applying the principle of gear reduction, which is well known and easily understood if one is familiar with the operation of a mechanical transmission with sliding gears. The automatic transmission applies the principle of gear reduction also, but instead of sliding gears, it uses one or more units known as planetary gear sets. A simple planetary gear set consists of three main components. The center component, shown here, is called the sun gear. In mesh with the sun gear, we find the planetary gears. These gears are connected to each other by a carrier. And finally, in mesh with the planetary gears and surrounding the whole assembly, we find the ring gear. The principle of operation of a planetary gear set is that it will provide gear reduction if one of the three components is held stationary. One of the components acts as the driving unit, and the third component acts as the driven unit. For example, let's say that the ring gear is locked in place and cannot turn. We will see later how this is actually accomplished in the transmission. Then let's assume that the sun gear is being turned and is driving the planet gears and their carrier within the locked ring gear. Then, for example, if a 3-to-1 gear reduction is desired, the gear ratios would be designed so that when the sun gear turns one complete revolution, the planet carrier would only turn 1/3 of a revolution. Now let's install this gear set into a transmission and see how it functions in practice. The first step is to initiate the transfer of power from the engine into the transmission. As explained previously, this process begins at the transmission fan of the fluid coupling or torque converter. The fan wheel is connected to the input shaft of the transmission, and the other end of the shaft is connected to the sun gear. Next, the output shaft is attached to the planet gear carrier. The only thing now necessary to provide reduction is to hold the ring gear in place. The input shaft must then turn 3 times before the output shaft makes 1 complete revolution. Once inertia has been overcome and the vehicle is moving, gear reduction is no longer required. At that point, the planetary gear set is locked up, which refers to the principle of locking 2 components together. When that is done, the gear set rotates as a single unit, and input and output shaft rotate at the same speed. Our example up to now described a simple 1 planetary gear set transmission designed to supply only 1 reduction. This would not be considered very efficient for modern automotive applications. In actual practice, 2 or 3 planetary gear sets are used in a modern transmission to provide 3 or 4 forward gear ratios. For example, if a 2 planetary transmission is used with 1 planetary providing a 2.5 to 1 ratio and the other providing a 1.5 to 1 ratio, 4 forward speeds are possible as follows. In first gear, both planetaries would be put into operation by locking 1 part of each gear set. An initial reduction of 2.5 to 1 is provided by the first set. This reduction is fed into the second set, which provides further reduction at a ratio of 1.5 to 1. The final output is the multiple of both reductions, or a first gear ratio of 3.75 to 1. This very low ratio is used to overcome the inertia of a standing vehicle. Now that the vehicle is moving, the very low gear reduction available in first gear is no longer required. A higher gear ratio can be applied. To accomplish this, the first planetary set continues to provide reduction. The second planetary set is locked up and turns as a unit. Consequently, the output shaft turns at the reduction of 2.5 to 1, provided by the first planetary set. A higher ratio can be utilized as the vehicle continues to gain momentum. In third gear, the first planetary set is locked up, and the second set provides a higher ratio of 1.5 to 1 at the output shaft. Finally, for fourth gear, when gear reduction is no longer required, both planetary gear sets are locked up. The output shaft turns at the same speed as the input shaft. We have now completed the explanation of how the second requirement of the transmission, providing gear reduction, is accomplished. The third and final function which the transmission must provide is a means of reversing the normal direction of rotation so that the vehicle can move backwards. The planetary gear assembly is ideally suited for this purpose. The process begins as before, with the transmission fan and input shaft turning the sun gear in the normal direction of rotation. The difference is in the next step. Since to reverse the direction of rotation, the planetary gear set is designed as the example shows so that the ring gear drives the output shaft of the transmission and the planetary carrier can be locked up. Utilizing this design, when the planetary carrier is locked up, the rotating sun gear drives the planet gears in the opposite direction. This reverse direction is transmitted to the ring gear. Since the ring gear is attached to the output shaft turns opposite the normal direction, and the vehicle moves in reverse. To review up to this point, we have explained the three basic necessities that an automatic transmission must provide. The first being a means of connecting and disconnecting engine and driveline. The second being a means of providing gear reduction in order to move the vehicle from a dead stop up to cruising speeds. And the third, providing a means of reversing the rotation of the output shaft so that the vehicle can be moved backwards. As we have explained, engaging gears in an automatic transmission is actually the process of controlling the operation of the planetary gear sets. Now let's see how this is actually accomplished. First, we will look at how one component is physically locked in place so that it cannot rotate. There are three major components which accomplish this. The first, as shown here, is called a brake band. The second component is called the brake band drum. The drum is attached to the part of the planetary gear set which is to be held in place. The third component is called a brake band piston. The brake band drum is mounted to rotate within the brake band. The band is wrapped loosely so that the drum rotates freely. The brake band piston is placed at the open end of the band. When hydraulic pressure is applied to the piston, the band is compressed and locks the drum and prevents it from turning. The component of the planetary gear set attached to the drum is held, providing gear reduction. The next point we want to look at is how two components of the planetary gear set are locked together. As explained previously, when this is done, the entire gear set rotates as a unit. To lock two components together, a clutch is used rather than a band. Internally splined fiber clutch discs are connected to one component of the planetary gear set, and externally splined metal clutch plates are connected to a second component of the planetary gear set. The plates and discs are arranged alternately in a clutch pack, and the clutch pack is mounted within a clutch drum. A hydraulic clutch piston is also mounted in the drum. As shown here, the piston is at rest, the clutch pack is not applied, and the individual components of the planetary set are free to rotate. When the hydraulic clutch piston is applied, it compresses the plates and discs together, and since they are connected to the planetary gear set components, the planetary set is locked up and must turn as a unit. Now that the mechanical means of operating a planetary gear set are understood, we can proceed with explaining the next point of interest. We will now take a look at the hydraulic operation of the transmission and the process of controlling when and how a clutch or band is applied or released. The first consideration must be, how is hydraulic pressure provided to operate a band or clutch piston? To provide the hydraulic pressure required, a simple gear pump is driven by the engine using two lugs on the torque converter. We will explain the hydraulic operation using a hydraulic schematic, and we'll begin by first inserting the pump and a clutch or band piston. As you can see, though, this arrangement would not work in practice, since the piston would be applied the entire time the engine is running. The piston must be applied at a specific time only, and the most important consideration is the speed of the vehicle. To provide the necessary information about the speed of the vehicle, a centrifugal governor is driven by the output shaft of the transmission. Pressure from the pump is directed to the centrifugal governor. Dependent on speed, flyweights operating against spring pressure position a valve which allows a certain pressure through. This pressure increases in direct relation to the increasing speed of the vehicle. The pressure created is called governor pressure. The governor pressure is routed to a command shift valve. The valve is a spool valve that has governor pressure pushing on one end of the valve and an opposing spring pressure pushing on the other end. With increasing speed, the governor pressure finally reaches a specific value, and the shift valve quickly moves to the open position. The piston applies and will remain applied as long as the pressure remains high enough to hold the valve in the open position. Governor pressure would be sufficient to control the shifting of the transmission if the vehicle was always operated under the same load and at the same rate of acceleration. But a vehicle is not operated under a constant load. In fact, a vehicle is operated under very different extremes. Therefore, the transmission must be capable of sensing the actual load and change the shift points accordingly. Changing the shift points to compensate for the load is accomplished by applying a hydraulic counterpressure against the command shift valve. This counterpressure opposes the pressure created by the governor. This load-dependent pressure is called control pressure. The control pressure is regulated by a valve which is operated by linkage connected to the accelerator, and therefore senses how much load is being applied relative to the position of the accelerator. To summarize, the command shift valve is under the influence of two pressures. One pressure is called governor pressure and is speed dependent. The second pressure is called control pressure and is dependent on load relative to the position of the throttle. Governor pressure is constantly trying to cause an upshift to take place as the speed increases and the governor pressure rises. Control pressure increases as the accelerator is depressed and is constantly trying to delay the upshift or cause a downshift to take place. The transmission shifts to either a higher or lower gear depending on which of the two pressures is greater. Up to this point, we have explained how speed and load determine when a band or clutch will be applied or released and cause a shift to take place. But there is one other important factor regarding shifting that should be understood. We should also understand the process of controlling the firmness of the shift. For example, if the vehicle is under no load and light acceleration, the piston should apply softly and somewhat slowly so that the shift is not harsh. Whereas if the vehicle is under heavy load or fast acceleration, the piston must apply firmly and quickly. This is necessary to prevent damage to the bands and clutches. To determine the actual load that the vehicle is under, a component called a vacuum modulator is installed on the transmission. It is connected to the intake manifold with a vacuum line and senses the intake manifold vacuum, and therefore the engine load. Depending on engine vacuum, the modulator positions a control valve within the hydraulic circuit. The valve will allow more or less hydraulic pressure to pass. This pressure is called modulator pressure. The modulator pressure is directed to a second valve called the working pressure regulator. The position of this valve is dependent on the modulator pressure, and accordingly, more or less pump pressure will pass by the valve. The pressure that passes by is called working pressure and is used to apply the band and clutch pistons. To illustrate, if the engine is under a heavy load, the vacuum will be low. The modulator valve moves toward the open position, allowing high pressure to pass. The pressure regulating valve is forced toward the open position. With the higher pressure, the band or clutch is applied firmly and the transmission is protected. Conversely, when engine load is light, the vacuum will be high. The modulator control valve will move toward the closed position. The amount of pressure going to the pressure regulating valve is reduced. The pressure regulating valve then moves to a position which allows less pressure to pass. The band or clutch applies softly, and a harsh shift is avoided. In this program, we have attempted to provide an understanding of the operation of the automatic transmission relative to the basic mechanical function and the related hydraulic operation. A previous knowledge of these basics will help in understanding the information to be presented in future programs, which will deal with testing and diagnostic procedures related to the automatic transmission. This concludes Automatic Transmissions, Principles of Operation. Another Education for Excellence service training presentation.